Heat transfer equipment is designed primarily based on heat transfer analysis. The heat transfer problems encountered in practice can be considered in two groups. The first is rating and the second is sizing. The rating problems determine the heat transfer rate for an existing system at a specified temperature difference, while the sizing problems determine the size of a system to transfer heat at a specified rate for a specified temperature difference. How could we enhance the heat transfer rate from a surface body? The rate of heat transfer from a surface at a temperature Ts to the surrounding medium at T infinity is given by Newton's law of cooling. A subscript S is the heat transfer surface area and H is the convection heat transfer coefficient. Based on Newton's law of cooling, when design considerations fix the surface temperature and surrounding temperature, there are two ways to increase the heat transfer rate, either by increasing the convection heat transfer coefficient H or increasing the surface area. How to enhance the convection heat transfer coefficient H? Increasing the convective heat transfer coefficient H may require the installation of a pump or fan or replacing the existing one with a larger one. Still, this approach may or may not be practical. The alternative is to increase the surface area by attaching to the surface extended surfaces called fins, made of highly conductive materials such as aluminium. Finned surfaces are manufactured by extruding, welding, or wrapping a thin metal sheet on a surface. Fins enhance heat transfer from a surface by exposing a larger surface area to convection and radiation. The convection heat transfer coefficient depends on the surface geometry, the nature of fluid motion, the properties of the fluid, and the bulk fluid velocity. Finned surfaces are commonly used in practice to enhance heat transfer. They often increase the rate of heat transfer from a surface several-fold. The car radiator is an example of a finned surface. There are a variety of innovative fin designs available in the market. In the analysis of fins, steady operation with no heat generation in the fin will be considered. The thermal conductivity K of the material and the convection heat transfer coefficient H are assumed to be constant. H is considered uniform over the entire surface of the fin for convenience in the analysis. Consider a volume element of a fin at location X having a length of delta X, a cross-sectional area of A subscript C, and a perimeter of P as illustrated. Under steady conditions, the energy balance on this volume element can be expressed as presented. In a symbolic form, is expressed as the following. Replacing the surface area of the volume and the convection heat transfer in terms of delta X, dividing the updated equation with delta X and delta X tends to 0, yield equation 353. Substituting the rate of heat conduction into equation 353 gives the differential equation governing heat transfer in fins, as shown in equation 355. In the particular case of constant cross-section and constant thermal conductivity, the differential equation 355 reduces to equation 356. Equation 356 is a linear, homogeneous second-order differential equation with constant coefficients. The general solution of the differential equation 356 is given in equation 358. C1 and C2 are arbitrary constants whose values are determined from the boundary conditions at the base and the tip of the fin. We need only two conditions to determine C1 and C2. At the fin tip, we have several possibilities, including infinitely long fins, negligible heat loss, specified temperature, and convection. In the following video, we will consider each case separately.